Okay, so now we talk about ultrafiltrations. We have talked about the selective reabsorptions. Always remember when the question asks about selective reabsorption, basically they refer to the PCT. Look at Henlé, not really. Okay, we talk about selective reabsorption. Our focus always at the PCT. Now the reason is in the loop of Henlé, we only reabsorb back the ions and water molecule. No more glucose, no more amino acid anymore. So that's why the selective reabsorptions, we always refer to the process that take place in the PCT. But don't get the idea wrong that, oh, there's no selective reabsorption in the loop Henlé, which is wrong because loop Henlé, we do have the selective reabsorption, but our focus here will be in the reabsorptions of the water molecule as well as the ions, the sodium and chloride ions. Okay, so let's look at these reabsorptions in the loop of Henlé. So reabsorptions basically in the loop of Henlé, our focus more to the water molecule. We do know that we still have about like 64, okay, 64, almost 65 liter of the fluid are still inside, right, in the loop of Henlé per day. So therefore, we need to reabsorb them back. Okay, so the reabsorption of water molecule in the tubular filtrate in loop of Henlé depends on the creations of the steep water potential gradient in the renal medulla. So why renal medulla? Because loop of Henlé found in the, we can find the loop of Henlé inside the renal medulla. Okay, so the system that create this, the system actually do this is the counter current multiplier system. So why we talk about the counter current multiplier system? Basically, we have the two limbs of the loop running side by side with the fluid flowing down in one and then up in another limb. So enable the maximum concentration of solute to be built up both inside and outside the tubule at the bottom of the loop. So this is how we create this, what we call the counter current multiplier. And in this case, we have to understand that the cell lining the descending limb permeable to water molecule. Descending. So therefore, water molecule can be reabsorbed back by osmosis. But the ascending limb, impermeable to water molecule. Are you clear? Impermeable to water molecule. So means that water molecule only can be reabsorbed back at the descending limb. Ascending limb, no. Water molecule cannot be reabsorbed back. Okay, so let's look at what is the mechanism of reabsorption in the loop of Henlé. A little bit complicated here. Okay, so let me draw out the process. Now, you have this PCT. Here, so this is PCT. So enter into loop of Henlé. And from loop of Henlé, make a U-turn. Okay. Then enter into the DCT. And then from the DCT, then enter into the collecting duct. Okay, this is how the nephrons makes. Okay, right. Okay, so we divide into the two regions here. The top region is called as cortex of the renal cortex. So bottom is the medulla. Okay, renal medulla. Okay, so because due to the reabsorptions of the water and also the, what we call these, the solute. So if you check the osmolarity, means the concentration of solute. Now osmolarity in this case is concentration of solutes. When before enter into the loop of Henlé, this is loop of Henlé. Okay, before enter is roughly about 300. Are you clear? About 300 osmolarity. Now, osmolarity is not a unit that we frequently use in our syllabus, but osmolarity in this case basically number of solute per unit volume of the fluid. So 300 you can assume is, let's say, something per ml, for example, we have 300 solute, which is not true, but you can imagine this way: 300 solute per ml. Okay, so we have ascending limb and descending limb. So what will happen here is, if you check the medulla actually have very high concentrations of the sodium ion and very high concentrations of the chloride ion. Are you clear? Very, very high sodium ions and chloride ion concentration. Okay, and if you check, it's about 4 times higher than the normal tissue fluid. About 4 times higher than normal tissue fluids, and it's gradually changed. What does it mean gradually changed? If I divide them into 4 regions, okay, in the medulla, okay, divide them into 4 regions in the medulla. And you realize that each regions, the osmolarity also very, very different. Okay, so for example, that the region nearer to the cortex, the osmolarity here is roughly about 600 units osmolarity. Then when you go down to the medulla, deep down to the medulla, you can see that the concentrations increase. You can see 800, 1000, and 1200. You can see that gradually change the osmolarity. So imagines that, if it imagines the fluid, sorry, here. Okay, here's 600 unit of solid compared to 800, 1000, and 1200. That means the solids, or what we call this osmolarity. Now, imagines that, because we do know that, okay, at the descending limb here, okay, permeable to water molecule. Okay, so means that osmosis will take place, right? Osmosis will take place. Now, how the osmosis actually take place? Right? It must based on the water potential gradient. Try to imagine, okay, 300 osmolarity. What is the water potential? If 300 osmolarity means that dilute cannot, only 300 particle per unit volume, but surrounding 600. So water molecule actually move out by osmosis. We reabsorb them by osmosis. Can you see that? So means that the osmolarity, okay, if you look at the formula, concentrations equal to the mass of solute versus the volume. Mass of solute remain the same, no change, right? Why? Because it's not permeable to the sodium ions, chloride ions, nothing can diffuse out, only water molecule. So means that now you can see that volume decreases, concentration increases. So osmolarity now from 300 become 400, become 500, and eventually become 600. Are you clear? It continue, right? Okay. Okay, again, it's from 300, okay, become 400 because loss of the water molecule, right? The volume decreases, concentration continue, the osmolarity continue. 400, 500, and 600, they reach what we call something like dynamic equilibrium already. Correct or not? Okay. But when it enter 600, enter into this region, can you see that? 600 compared to 800, nothing. 600 is still dilute. So water molecule continue to be reabsorbed back. Can you see that? So osmolarity increase, the number of solute increase. Correct or not? Mass still the same, but volume keep on decreasing. So concentration now continue to increase. Okay, 600, 700, 800. Oh, reach a dynamic equilibrium. Then enter to the next region. Water molecule reabsorb back. So means that continuously until the what we call the tips here, you will get a very, very concentrated, a very, very concentrated filtrate now at this region. So we have a very concentrated filtrate. Are you clear? So here you may have a question. Why so troublesome? Make ingredient 600, 800, 1000, 1002. Can we straight away start with 1200? Easier, right? 1200, then everything will be settled. Okay, no need to go through this step by step. The answer is no, because if you compare 300 and 1,200, 300 is so dilute, 1,002 is so concentrated. Water potential here is much more higher, too high compared to this. So if you don't do it gradually, your or our loop of Henlé cells will burst, because that is too steep, the gradients of this water potential gradient. At the end, water actually enter into the loop of Henlé cell, burst the loop of Henlé cell immediately, because too steep. Are you clear? Too steep. So that's why we need to do it gradually. We need to do it gradually. Are you clear? Okay, we have to do it gradually until 1,200. So the question here is how we can create these high concentrations of the solutes inside the tissue fluid. Then it depends on the ascending limb. Ascending limb now no longer, ascending limb no longer permeable to water molecule, but we do have the active transport of the sodium ion and the chloride ion. Okay, we have the active transport of these ions. Now, why we need to transport out the sodium ion and chloride ion? The first reason, definitely we want to reabsorb back the sodium ions and chloride ion. Another reason here is, if you look at the cortex region here, the osmolarity at the cortex region is roughly about 300 units. So if we don't do anything to pump out the sodium ion and chloride ions, this 1,002 will remain the same and all the way enter into the DCT. What will happen? You try to imagine. Inside is 1,200. Outside 300. Water potential is low. Water potential is high. Inside, water potential is low. And water molecule going to rush in. Then what's the point? We reabsorb back water molecule and then allow water molecule to rush back. So which is something that we don't want. Are you clear? So what will happen here is, now, because at the ascending limb, okay, impermeable to water molecule. And this is very concentrated, right? We don't want to add water molecule in, okay? So again, look at it. Concentrations equal to the mass over volume. Because we cannot reabsorb back the water molecule, therefore, water volume remain the same. The fluid concentration remain the same, no change. But we can, in order to decrease the concentration, so that we can increase the water potential, therefore, one of the way we remove solute. So these solutes, they are sodium ions and chloride ion. Can I see that? So means that from 1,002, if you remove the chloride ions, sodium ions, what will happen here? From 1,002 become 1,000, become 800, become 600, and slowly when enter here, actually, it become roughly about 100 osmolarity. So if you look at this, if here's 100 at the DCT, the difference is not so huge. That's one. Second, if 100 means that water potential is still higher compared to the surrounding. So continuously, we can reabsorb back the water molecule. Are you clear? This is how we reabsorb back the water molecule in the DCT, because we pump out sodium ion and chloride ion, making them low in the solutes. When low in the solute, basically higher water potential. So means that water molecule can be reabsorbed back in the DCT, okay? But later, what you can see here, guys, when the filtrate continue to enter into the collecting ducts, all the way enter into the medulla regions, same thing happen, similar to the descending limb of the loop of Henlé, because here 600. Can you see that? Because 600, and then 800, 1,008, and 1,200. So what will happen here is, can you see that 100 slowly, because reabsorption of water molecule, the osmolarity become 300. When drop to here, we can reabsorb back the water molecule again from 300 to become 600, 800, 1,000, and 1,002. So at the end, what we can produce here, we're going to produce the urine at the end. So this urine will have low volume, high concentration of solute. Are you clear? At the end of the process, we produce a urine with a low volume. How much? Roughly about 1.5 to 2 liters per day. At the end of the process, we're going to have a low volume of the urine with high concentrations of the solute. Get the idea? Okay, so I repeat again. Okay, I repeat again. So what is the way to make this high concentrations of the ions in the medulla tissue fluids? Basically, because of the at the ascending limb going up, ascending limb, constantly we use ATP to pump out the sodium ion and chloride ions. So about 4 times higher. You compare to normal tissue fluid, 4 times higher. Are you clear? So when the filtrate enter into the loop of Henlé or descending limb, water molecule will be reabsorbed back by osmosis down the water potential gradient. So it means that in making the filtrate become more and more concentrated at the tips here. Are you clear? At the tips here, so the concentrations of the filtrate is very, very high. But we can decrease the concentration when the filtrate move up the ascending limb of the loop of Henlé, because constantly we pump out the sodium ions and chloride ion. Until when this filtrate enter into the DCT, the concentration of solute is so low, water potential is still high, water molecule can continue to be reabsorbed back in the DCT, and then all the way enter into the collecting duct. So when it goes into the collecting duct, what happened here is the fluid or the filtrate experience the same thing that happened in the descending limb of loop of Henlé. So water molecule continue to be reabsorbed back in the collecting duct until we produce the urine, which is low volume and with the high concentrations of solute. It depends also with the hormones. We're going to discuss it when we on Thursday, where we're going to look at the osmoregulation. Here, we don't talk about osmoregulation yet. We talk about the normal process when you produce the urine roughly about 1.2 to 2 liters per day. Okay. So what you need to explain when talk about the reabsorption in the loop of Henlé. So against at the ascending limb, we pump out sodium and chloride ion. Okay. At the descending limb, we have allowed the osmosis to take place. So means that at the descending limb, we make a high concentrations of the filtrate, but after that, we remove the solute to make it become low concentrations, allow the continuous reabsorptions of the water molecule inside the DCT, and then later collecting ducts. Okay, so you can try to arrange the following events in the correct order. Okay, this is the answer. We can try. Now next, the fluid that's flowing up the ascending limb of the loop of Henlé lost the sodium ion and chloride ions, so become more dilute and having higher water potential. This is very important. Why? Because we want to continue to reabsorb back the water molecule. We don't want the water molecule to reverse way, enter back to a DCT. So therefore, they have higher water potential. Okay, there is one study talking about the deserts, okay, desert rodents, where they have very, very long, what we call this, a loop of Henlé. So means that if you look at this here, if we have longer, we can make it even more higher concentration, 1002 if we go down, 1005, 1008, 2000, okay? So because they survive in the desert, means that they lack of the water supply. So they need to conserve more water. They want to reabsorb back water. One of the way is to make the loop of Henlé longer. So that is a correlation. Again, there's correlation to show that the less, the what we call this, the less supply, those animals that can survive in the desert, their loop of Henlé relatively longer compared to those that survive in the place that have enough water supplied. Okay, so this is possible because the medulla is relatively large and the medulla is long. So the cells that line the ascending limbs have deep infold with many sodium potassium pump and continue to pump out the sodium ions. And the cytoplasm is filled with many mitochondria to pump out the sodium and potassium ion into the medulla. So making medulla very, very concentrated. I mean the ion concentration, and also make the water potential of the medulla is so low that desert rodents will be able to reabsorb back the water, I mean with higher efficiency. Okay, so with this, I stop for today's class.